We've been talking this semester about kinetics and rate constants, and today we'll look at how we determine the enthalpy and entropy of activation, these parameters associated with the activation barrier for a reaction. The Eyring equation tells us what factors govern a rate constant. There are a number of parts of this equation. So there's what's called a pre-exponential part and an exponential factor. And the pre-exponential part contains temperature information as well as a number of constants. There's Boltzmann's constant, Kb, that converts temperature information to the energy of an individual molecule. There's Planck's constant, h, that relates energy to frequency. And there's this term kappa that's usually considered to be 1, which says how often, how frequently when a molecule arrives at the transition state, how frequently does it go ahead to products? And we usually assume it happens all the time. The second part of the equation, this exponential part, is the part that we're really mostly interested in. And that's the relationship between the activation energy, which is the amount of energy needed to get over the barrier, and the temperature, which is sort of an index of the amount of energy available to the reaction. And there's a factor of R there. R is a lot like Boltzmann's constant. It's the ideal gas constant. It relates the amount of energy in the molecules to the temperature available. So if we graph this relationship, we get a curve like this, and it's an exponential curve, and because of the negative sign in the exponent, it flattens out as we go to higher and higher temperatures. Now, if you want to use that curve to figure out things like the enthalpy and entropy of activation, that's a little difficult. People don't like these curved relationships. They prefer to work in linear terms. And so here's a linear treatment of the Eyring equation. And what we've done in going from one to the other is, well, a few things. First of all, we've divided by t on both sides here. So the t's cancel out here, and we get a k upon t factor there. We've also expanded delta g into delta h minus t delta s. And that's how we get these two terms here and here. And then to get rid of this exponent, we just took the natural log of both sides. And of course, when we take the natural log of something that contains an exponent, the natural log and the exponent are opposites of each other. They just cancel out and disappear altogether. So we just get natural log on the left side, natural log in front of all those constants from the pre-exponential factor, and delta h and delta s are just left without any exponents, without any natural logs. Now, the reason to do this again is because what it gives us is a straight line when we graph it. And the form of this equation looks like y. That's what we're plotting on the y-axis. Natural log of k upon t equals mx, because x here on the lower axis is 1 upon t, and then this is plus b. So we get this part from the intercept, we get this part from the slope, and we learned how to handle something like this in, I don't know, junior high or something. So we can take the slope, and from the slope we can determine delta h. We just multiply it by minus r. And we can take the intercept, and if we know all those constants, we just factor those out, and we get delta s. So that's how we determine the energy, the free energy of activation by determining the enthalpy of activation and the entropy of activation.